These kind of equations, well, let's see. Number one, let me give you a preliminary example. If I have this graph right here, the question is, well, oops, function or not a function?
Not a function.
Why not?
Does it pass the vertical line test?
It doesn't pass the vertical line test, right? I mean, crosses more than once. And what if this graph is describing position versus time? Essentially, we are at two different positions at the same time. Like we are in class at the same time, but we are at the beach getting some margaritas, getting tan or something. Is that possible? Not yet, right? I don't know. Maybe in the future it's possible, but not for now. All right. But what if I told you that indeed, oh, shit. Okay. What if I told you that this is a function depending on how you describe it, on how you design this function? Well, what do I mean by that? Well, so what if this is the trajectory of some particle? You know, and you may have seen this before. I mean, I don't know if you guys have been to the Miramar Air Show where these military airplanes do these pretty cool maneuvers. They go high speed, you know, doing these maneuvers, and they go upside down. You know, basically they're following that trajectory, right? But the question is the airplane in two different places at the same time? Yeah. No. It could be in the same value of x, I mean in the same position x at different times. That is, in this case, the position of the airplane, say at t equals 0, after 0 seconds, after 1 second, 2 seconds, 3 seconds, etc. So in this case, this is a function, however, it's parameterized, or it's rather governed by a third-party variable in the background, and that third-party variable in the background is time. So in this case, we have different order pairs at different times, and that's a good way around to describe this sideways parabola as a function. So, and well, where have you seen this kind of paths before? For example, when you read a map, whether this is a printed map in paper or Google Maps, you want to go from point A to point B along the road C, you know? And well, what Google Maps does, for example, is to find the most efficient route, you know, the one that takes you through to where there's less traffic and actually makes you spend less gas. It's a pretty cool app nowadays. Well, so the road that the Google Maps is going to draw is something like this, that otherwise, if you do the vertical line test, well, it's going to fail. However, well, you're not going to go in 3 different places at the same time. It's actually this path given by Google Maps, for example, is describes position of a particle, one in this case our car, at different times. Okay, and in this case, well, that's still within the real laws of physics, you know, that that we cannot be in 2 different places at the same time. Okay, now how are these equations going to look like? Well, this set of equations are going to look like a system of equations in which x and y are both functions of time. Well, for now we're going to look at the 2-dimensional case. In this case, the 2 equations with a parameter in the background. However, next semester in Calc 3, you're going to look at these parametric equations in 3 dimensions, you know, to parameterize a curve or a line segment using 3 parametric equations. But well, that's going to be Calc 3. All right. So let's look at an example. How do we graph them? How are these functions similar to the graph that we are used to graph already? And how are they different, most importantly? All right. Well, So for the first example, they're asking us to identify the curve defined by the set of parametric equations, x equals t squared minus 2t, y equals t plus 1. And well, something I forgot to type here. Then eliminate the parameter. And this, so we can identify the graph of this. And I mean, we can sort of have an idea by looking at the equations. Well, there's a quadratic in there, so it looks like some parabola might be involved in here. But well, let's find out first. So number one, when you guys learn how to graph equations, whether they're functions or not, because I mean you can still graph ellipses, circles using a table of values even though they're not functions. So whatever we do for tables, it's not limited to functions, it's just in general to equations, rather relations. It's a relation of points, and a function is a special recall that a function is a special relation in which every single input has only one output. If it has more than one output, it's no longer a function. It's still just a relation of points. All right. So this is what we're going to do. So this time, instead of making a table for x, y, that is, we give values to x to plot to find out the outputs y. This time, these points order pairs, these order pairs right here, depend on time, depend on a different value t. So that is, what we're going to do here is for the different values of t, we're going to plug them in both equations and obtain the result, obtain the order pairs. For example, at t equals to 0, plug in t equals to 0, whatever you see in the letter t in the parametric equation. 0 squared minus 2 times 0, of course, that's 0. 0 plus 1, that's a 1. That's going to produce the order pair 0, 1. So that is that the initial point when t equals to 0 the particle is at the point 0, 1. Let's see what happens after at t equals 1. And in this case, again, we don't know whether these t's represent seconds, minutes, years, even. So that doesn't matter for now. We don't have any actual context. I mean, any physical context, you know. So let's see. T equals 1. That is 1 squared, which is 1, minus 2 times 1, which is negative 2. 1 minus 2, isn't that a negative 1? And 1 plus 1 is 1. Oh, actually, no. 1 plus 1 is 2, not 1. What the hell? I know. So 2. 2 squared minus 2 times 2, that's 4 minus 4. Isn't that a 0? And 2 plus 1 equals to 3. 0, 3. That produces the order pair 0, 3. And what else? Number t equals to 3. 3 squared, which is 9, minus 2 times 3, which is 6. 9 minus 6, isn't that a 3? And 3 plus 1 equals 4. That produces the order pair 3, 4. And last but not least, for t equals to 4. So that's t to the 4th power, which is 16. Over here, minus 2 times 4, which is 8. 16 minus 8, isn't that 8? And 4 plus 1 equals to 5, producing the order pair 8, 5. So we have order pairs to plug in, or rather to plug in the Cartesian plane. Let's see how is that going to look like. So, in a way, this is somewhat the similarities in how we obtain order pairs in this case by plugging in a value of t. But actually, we plug that in into two equations, not just one. So let's graph. So negative 1, 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8. Okay, and let's plot these order pairs. So the first order pair 0, comma 1. The second order pair, negative 1, comma 2. The third order pair, 0, comma 3. The fourth order pair, 3, comma 4. And 8, comma 5. All right. So these are the order pairs produced by this table here, by this set of parametric equations. Okay. So let's see. Now, what's the difference this time? So back when we were plotting graphs of equations or plotting equations by plotting order pairs, we never had a rule to go, oh, first plot the point corresponding to x equals to 1, x equals to 2. So in that situation, you have a freedom of choice. Like I can plot the order pair related to whatever x equals to 3 first, and then I can plot the point related to x equals to negative 7 if I want, and then go back to x equals 75 million, whatever order pair. There was really no rule to go in order, but usually we got these tables 0, 1, 2, 3, or negative 2, negative 1, 0, 1, 2, 3, just to have an idea of how the graph looks like, around the origin of the Cartesian plane. But that was not really a rule. However, here it is a rule. And in this case, well, number one, let's plot the points and let's have a sense of direction. So notice this is t equals to 0, 1, 2, 3, 4. So I'm going to go in this order. All right. However, well, how am I going to anyway denote? Because you guys already saw how I draw the graph in this direction. But what if you guys blinked or something, or were looking somewhere else, and well, you missed that part of the direction? In this case, that's the extra part in parametric equation. We need to label that sense of direction. Number one, and there's two ways to do that. Number one, okay, put the arrows to indicate the direction, and also label t equals 0, t equals 1, t equals to 2, t equals to 3, t equals to 4, etc. Right? This is going to give us a sense of direction with respect to time. We didn't get that back when we were graphing equations in the Cartesian plane without a parameter, without a third-party variable or a third-party parameter governing this set of points. This time we have. Well, they're asking us to identify the curve defined by this parametric equation. Well, clearly by looking at the picture, it's a parabola opening to the sides. And however, when they're asking us to eliminate the parameter and describe that equation without having t's in it, that is, just having the equation using x's and y's. How are we going to do that? Well, look at the pair of equations and identify the easiest of the equations. And well, to me, the easiest of the equations is the second one. What are we going to do with that equation? Solve for t. Whatever you get, substitute it back in the first equation. So this is what we do. So if y equals to t plus 1, that means t equals to y minus 1. All right? And in this case, well, let me go back to the first equation, x equals to t squared minus 2t, for which we're going to substitute the variable t here and there. Just substitute y minus 1 squared minus 2 times y minus 1. And well, we just obtained an equation without the parameter t. So we just eliminated the parameter. We obtained the equation in Cartesian form, the xy, without an equation for which we plot order pairs without following any order, that without a sense of direction as opposed to the parametric. However, let's simplify this. So that's y squared minus 2y plus 1 minus 2y minus minus, that's a plus 2. And simplifying this, This is a function x of y, if you will, so that's y squared minus 4y equals, minus 4y plus 3. And does that look like an equation, like the equation of a parabola? Yep, it looks like the equation of a parabola. And well, it opens to the sides because in this case the quadratic term is the y variable. Otherwise, if we had a y as a function of x, we would either obtain an equation, or rather the graph of a parabola, either opening up or opening down. When we have a parabola in terms of y, we get a parabola either to the left or to the right. Well, in this case we got it to the right because the leading term is positive. Okay, let me make this look like a y. All right. So that's one example. The preliminary example, if you will, so we can see all the differences between graphing equations in Cartesian plane and in parametric form, which there's a lot of similarities, but there's a little extras here. Those couple of extras here is we need to denote the sense of direction by either using the arrows or labeling t equals 1, t equals 2, etc. All right. Of course, we can parameterize pretty much every single equation, every single function. So we're going to focus on parameterizing circles in the next couple of pages. And I don't think we're going to have enough time today to parameterize equations of lines, which is going to do something we're going to do next time. All right. So example number 2, what curve is represented by the following set of parametric equations? In this case, x equals to cosine t, y equals to sine t over the intervals between 0 and 2 pi. So, well, one way to determine what this will be is to eliminate the parameter. But how did we eliminate the parameter in the previous example? So we went to the easiest equation, solve for t, whatever you get, plug it back in the first equation. Let's see if that is going to work over here. So if I solve for t on the x equation, t will be arc cosine of x, all right? And plug this in here, that'll be y equals sine of arc cosine of x. Are you familiar with this function? Do you know what the graph of that looks like? This is crazy. I mean, even though this what I did, it's not wrong, it's not the right way to describe it. In this case, we're gonna do something else. And actually, we're gonna make a pretty cool connection with something that you know. I mean, consider this set of parametric equations as sets of order pairs for which the x is cosine and the y is the sine. Does that ring a bell? What is that? What can you relate that with? Circle for which the x values in the order pairs are the cosine and the y are the sines, right? However, we need some sort of a transition equation to go from the parametric to the rectangular, of course. I mean, so x equals cosine, y equals sine. If we use the equation of the circle x squared plus y squared equals to 1, this means we can go about number 1, cosine, or rather, let me do it in steps actually. X quantity squared plus, I know this is kind of silly, but that's so we can plug in the corresponding values of t. That's cosine t squared plus sine t quantity squared equals to 1. And while just squaring both terms, that's cosine squared t plus sine squared t equals to 1. Isn't that an identity? The Pythagorean identity. So this is how we will relate the equation of a circle. Well, for now it's the unit circle, but we're going to look at circles of other radii and even centered somewhere else other than the origin. All right. In the meantime, so yes, this is the equation. So this is how we go to describe x squared plus y squared equals to 1. All right. Well, I mean, this is just the description, or rather the process to go back and forth between parametric and rectangular. But what about the graph? And well, what about the graph? Let's graph a circle. This is a unit circle. However, oops. What do we need to add in order to show a sense of direction of this parametric equation? Because in this case, we're not just plotting points for x and y. We have a particle either moving counterclockwise or moving clockwise, either one. How are we going to know? Well, for a few minutes, I'm going to go to my graphing calculator here. So, let me clear everything. How do I get the parametric form? So for those of you who have a TI calculator, on the mode menu, you might want to make sure that, well, number one, you're in radian mode, and there's the form mode function for the usual graphs, f of x, y equals f of x. Parametric form, which is what we're going to do today, and well, later we're going to look at the polar mode to graph functions in polar mode. So in this case, we have the parametric mode, and well, instead of having the function y equals f of x, well, notice this time the screen is going to give us two equations connected. That is one equation for each of the parts of the parametric equations, for which I will type cosine t and sine t. And sine t, all right? So let me change the, okay, that's fine. Second quit. Okay. So let's graph. Okay, be careful here. Whenever you're graphing parametric equations, make sure not to blink, because if you blink, you will miss the sense of direction of the graph right here. So let's see what's happened. Okay. Well, were you able to see the direction here? Did you guys blink? Even if you guys didn't blink, it was kind of hard to see. For me, it was kind of hard to see. Well, how do I turn this into a slower motion? Well, so I'm going to go to Window, and I'm going to modify the T-step. This T-step is the amount of points that the graphing calculator is going to plot. In this case, instead of having a T-step, okay, let me see what happens when I do one. Okay. I wasn't able to see what went on. So in this case, we did a smaller number, not 0.1, because we already got that part, and it was too quick. What about 0.01? Much better, isn't it? Yep. It goes slower, and you will be able to. You can even blink in this case, right? So you can even blink and still see the sense of direction. So let's go back over here and put arrows to denote that this is going on in the counterclockwise direction. And again, I mean, you could relate these parametric equations and connect it with your trigonometry knowledge. You know that every point is of the form cosine theta sine theta. I mean, technically I should have used t because of the parameter t, but I mean, you're used to the unit circle as angles theta, but it's the same. The x component is cosine, the y component is sine. All right, which is what we have. And in this case, we read the unit circle in the counterclockwise direction, don't we? All right, and well, let's do some comparison here and also graph its rectangular version. Well, for the rectangular version, I think it's pretty straightforward if we just graph the y equation, because y equals to sine. We know what the graph of y equals to sine looks like. Let me find the period. I know it's kind of silly to write down the calculation of the period, but I mean, I'm going to do it because it's going to be, we're going to do some contrast in the next example. So the period, which is 2 pi over b, where b is a number that multiplies the variable t inside of the angle of the function. In our particular case, b equals to 1. So 2 pi over b, 2 pi over 1, which is 2 pi. That means that the graph of sine will be graphed or rather will have a period of 2 pi. So let's see. Okay, no, that's fine. So, oh yeah, yes, I need it. So let's do the shape of a sine function. One cycle, it completes one cycle between 0 and 2 pi. All right? So I know it's kind of silly. I mean, we're just looking at the coefficient. I mean, just look at it. It's 1. Why do we calculate? Just do the graph. Well, I'd rather do it so you can see the difference in the next example. Is there anything else? Okay, no. I think that's about it for this example. Example number 3. What curve is represented by the following parametric equations? And number 1. Okay, let me have both in the screen. What do you notice different between this set of parametric equations in example number 2 versus the set of parametric equations in example number 3? So the order is reversed. Number 1. There's another difference here. The 2 in the coefficient of the angle, right? In this case, it's a 2. So let's find out what's going to be the difference here. Well, first of all, let me use the Pythagorean identity. Okay, I'm gonna start backwards this time. Well, actually, I'm gonna start the way I should have started the previous example. So usually, the trigonometric identity sine squared t plus cosine squared t equals 1. So this identity still holds regardless of the coefficient of t. If you have a 5t, just make sure to have a 5 and a 5 over here on both terms. Okay? The identity still holds if you have a sine of 5 million t plus cosine of 5 million t. It still holds. Sine squared 17t plus cosine of 17t cosine squared, right? It works for whatever coefficient. In our particular case, sine squared of 2t plus cosine squared 2t equals to 1. I'm going to write it the following way. In parentheses, sine 2t, cosine 2t. Okay, but what do we know about this? X equals sine 2t and y equals cosine 2t. So we can go back and replace the corresponding parametric functions with their corresponding variables, x squared plus y squared. And again, what do we have? The unit circle, isn't it? Which is the same unit circle as this unit circle in the previous example, right? However, in parametric form, these two unit circles are different. It's not like in rectangular coordinates, in the xy coordinates, you were able to draw the circle in your favorite orientation or in your favorite order of plotting the points, doesn't matter. But in this case, it's going to make a huge difference. So, okay, number 1, let me draw the circle. It's the unit circle again. However, things are going to change. So what changes this time? So let me clear. So we have sine 2t and cosine 2t. Okay? And well, make sure not to blink. And I'm gonna hit graph. What happened this time? It went the other way, right? It went clockwise. Did you notice anything else? Huh? Well, yeah, about the oval thing, well, let me just make that's a good observation. So, because of the aspect ratio of the graphing calculator, which is not 1-to-1, this circle is going to look like an oval or like an ellipse. So, I mean, it's still a circle. However, okay, let me zoom it in so you can see what else, so what's going on really. So, There's a couple of things. So number one, okay, you guys already identified that it went clockwise this time, okay? But there's something else going on. Oh, wait a minute. Zoom in. Did you notice anything else besides? Yes. It went more than once, right? It's not really easy to see that, right? Okay, let me do zoom standard again. Oops, no, zoom standard. And let me do zoom in again. So in this case, don't blink so you can see what's going on. Oh, well, it didn't happen. Oh, actually, let me do the t-step 0.01. I think it's going to be a lot easier to see. That's once. And it happens a second time. Did you guys notice that? It's not that clear to see, but it actually happened. Why is that? And how is that related to the equation? Exactly. And in this case, we're graphing over 0 to pi. So how many periods are going to have between 0 and 2 pi if pi is the period in this case? Isn't it twice? Okay. Let's describe that in paper. So number one, I'm going to find the period, which is 2 pi over b. That is 2 pi over 2, which is pi. That means the graph of sine in this case, or rather, actually y equals cosine, not sine. I think in the earlier section I did the sine function, not the cosine. Here I'm going to do the correct one. So y equals cosine 2t. Well, that's one cycle at pi because that's the period, and then another cycle at 2 pi. Well, this is in the usual way, in the Cartesian way that we're used to look at the graph of y equals sine or cosine, the wave functions. However, in parametric form, well, number one, over here, it went clockwise. However, traversed twice, as opposed to the previous example. Let me note that. Traversed once. All right? Now, question for reflection. So, what if we want to design a path to have a particle go around the circle 5 times? In this case, yes, clockwise in this case, be specific. What do we have to modify on this set of parametric equations to make the particle go 5 times around the circle? What about the b term? Or factor, rather. Yeah, but what do we have to do make it a 5, right? It would have to be a 5 on both equations, all right? So, that's the difference between the two. Similarities, differences. Let's look at number 4. For number 4, well, we go back to the order cosine and sine. However, that coefficient of 2 is no longer inside of the angle. In fact, is the coefficient of the trigonometric functions. And well, one thing that you might recall from shifting and transformations of functions is that the coefficient is a stretching factor. In the particular case for trigonometric function, that changes the amplitude of the trigonometric function to go, in this case, from -2 to +2. And well, also traverse once, because from 0 to pi, the period is pi. Let me plot. Let me get the period 2 pi over b, which is 2 pi over 1. And that's a period up to pi. But in this case, the amplitude equals to 2. That means we're going to have the function to go between -2 and +2, as opposed for the function going from -1 to 1. All right? But now, how is that going to change the look of the equation when we go from parametric to what's that? To rectangular? Well, number one, I'm going to rewrite the two equations. X equals to 2 cosine t and y equals to 2 sine t. So cosine on the one hand is x over 2 and sine equals y over 2. So number one, let's start with the trigonometric identity, the Pythagorean identity, the one that tells us cosine squared t plus sine squared t equals to 1. Well, let me do some mini rearrangement here. Put it in parentheses. Put it in parentheses. I know it's kind of silly to do this, but I think it's going to make it, it's going to make more clear about the substitution that we're going to do. So in this case, I'm going to replace cosine t, which is x squared over here, and sine t, which is y over 2, which is, hold on, where's the sine? Here. Whoops. Sine. And that's going to be here, all right? So, in this case, we're going to have the quantities x squared, or x over 2 squared, plus y over 2 squared equals to 1. And, well, square both numerator and denominator. That's x squared over 4 plus y squared over 4 equals to 1. And that's x squared plus y squared equals to 4. But, well, what is that equation describing? Yes, it's still a circle. But how is the circle different from the other one? A radius of 4, radius of 2. Recall that this number is the radius squared. So that is, in this case, it's 2, negative 2, negative 2 to 2. If we go to the parametric equations, let me clear all this. That's 2 cosine t and 2 sine t graph. It's now a circle of radius 2. Well, it looks like an ellipse. It looks like an oval, and it's also oriented counterclockwise, all right? And for the last few minutes, sense of direction. So we're going to generalize this. So we're going to find a set of parametric equations for the circle centered at HK and has a radius of r. So let's start with the equation x minus h quantity squared plus y minus k squared equals to r squared. Well, the trick to get from the rectangular equation to the parametric equation is to make sure that we have a 1 on the right hand side of this equation, because we're going to rely on the Pythagorean identity, cosine squared plus sine squared equals to 1. So we want a 1 on the right hand side of the equation. So what do we have? Quantity squared over quantity squared. How about the whole quantity, x minus h over r, quantity squared. And, well, we could. Well, in this case, I'm going to describe the counterclockwise version. So let this guy be our cosine t, and let this guy be our sine t. Of course, you can do the same by reversing the order and get the clockwise orientation here. So from here, we're going to set two equations: x minus h over r equals cosine t, and y minus k over r equals sine t. So in this case, I'm going to solve for x and y on both equations. I'm going to multiply both sides by r. That's going to give us x minus h equals r cosine, and x equals r cosine t plus h. Similarly, for that second equation, y minus k equals r sine t, and y equals to r sine t plus k. So let's write this as a set of parametric equations, the correct way, like a system of equations. X of t equals to r cosine t plus h, y of t equals r sine t plus h. And well, so that's in general how to parameterize a circle oriented counterclockwise. Let me note that. Let me denote that actually. Counterclockwise orientation. So in this case, that's going to describe any circle in a counterclockwise direction. Yes?
Y of t r sine t plus k.
Oh, yes. Where's the k here? I forgot the k. Yes, thank you. I think looks like I wrote the h twice. Okay. Okay. Well, how about an example? How about x equals 3 cosine t plus 1, y equals 3 cosine t plus 2. So that's a circle of radius 3 because the coefficient of the trigonometric functions is 3 and it's centered at the point 1 comma 2. Let's see if that's true using our graphing calculator. All right, so 1 and 2. So did I make a mistake? Oh, come on. Yes. Thank you. All right. Okay. So that's 3 cosine t, and oops, that's plus 1 and plus 2. So we should get a circle centered at the point 1 comma 2 with a radius of 3 and traverse the ones in the counterclockwise direction. Let's see. Well, I need to fix the window here so we can see the whole thing. So zoom standards, and that certainly looks like a circle having the center at the point 1 comma 2 and the other bits that we just discussed about it. All right.